Hello everybody, and welcome to the second video in the Vulkan game engine series. I should say second live stream. So today we've got a lot more ground that I want to cover. So one of the very first things that I was actually asked was if I could maybe put together a couple of quick charts just to kind of visually describe how all this stuff is going to go. So I've thrown together a very quick and dirty set of charts here to sort of describe some of this. So we've got a few different sections. We have our core section, which contains our logger, our engine, and our platform. The logger is pretty obvious. The engine is basically going to be what controls everything. It's a class that will control things such as the platform layer, the renderer, eventually the physics system, the audio system. It'll have links to all those things and control them. And then the platform layer is for anything that is platform specific. So that is things like the windowing system, things of that nature. And so the objective there is to basically abstract everything that is platform specific, including eventually file I/O through this platform layer. File I/O is probably a system I'm going to put in a little bit. I don't think I'm going to get to that today, but just so you guys understand the intent of those things. We're then going to have the renderer, which is kind of split up into these two sections. We're going to have a renderer front end, which holds things like materials and meshes, things of that nature, also lighting information. And those will be processed in a renderer API or graphics API agnostic way. So it won't matter to the renderer front end what backend we're using. And the backend, in this case, is Vulkan. But my idea with this engine eventually is to support more than just Vulkan. I'd like to put in an OpenGL fallback for platforms that maybe don't support it, as well as maybe even DirectX at some point. And so I want to be able to basically swap out backends and not have the engine or the front end be affected by that. So the back end will contain all of the graphics API specific stuff. In this case, like the Vulkan renderer, certain methods of this will be exposed through an interface that we'll develop later. And then things like utility classes and all of the texture classes, things of that nature. I'm not really going to fill all those out right now because we are developing this engine on the fly. So I don't sort of want to plan myself into a corner, if that makes sense. So at least on the high level, there's a lot of systems missing here. There's obviously, like I said, physics and audio and things of that nature, just to name a few. But it's basically going to be split up into modules like this. So the next thing I want to show is the startup sequence. So we'll have our main method, which will create a instance of an engine, which that's already doing. The engine will create a platform instance and a renderer instance. And then after those things are created and eventually the audio system, et cetera, we'll call engine.run. And engine.run is ultimately what kicks off our game loop. Our game loop in this case is managed by the Windows system. So it's actually, it resides in the platform layer. So we have this start game loop method that actually contains our while loop. And speaking of our while loop, oops, I named this startup sequence. This is actually the loop sequence. So we are going to have this this platform while loop that I described just a second ago. And in that, we're going to have a few different things that happen. Early on, it's just going to be input event handling. And then we're going to have a callback to engine.onloop. An engine.onloop will call all of the things that it is responsible for managing. So, for example, it'll update the physics, it'll update the world, it'll update the audio, and of course, it'll call renderer.draw. And this renderer.draw method is actually where we're going to be drawing to the screen. So I hope all of that makes sense. With that, let's move on. So one thing that I think I forgot to point out in the last video was I actually do have a GitHub repo for this. So it's at github.com/TravisVroman/regen. That may wind up changing if we rename the engine, but for now, that's where it resides. So if that changes, I'll let you guys know. But you guys can grab the source code here. I'll be uploading it after every stream. So when we're done with this stream, I'll go ahead and push that. Cool. So let me check the chat real quick before we jump into this. Hey guys, DirectX, OpenGL will be cool. Yeah, I think that that's going to expand the number of platforms that we can support. I'd like eventually to support maybe Android and things of that nature. Of course, that's way down the road, but having access to those different things would be huge. Are you going to write physics engines on your own? Use Bullet or physics open source ones? Okay, so this is probably one of the sections of the engine that I'm actually not going to write from scratch, because there are really good physics libraries out there that are super efficient, that can write way more efficient code than I'd be able to write in terms of physics. I'm not a physics expert. I'd have to do a lot of research in order to write one of those on my own. I've never written a physics engine. And so in this case, I'm probably going to use... I'm leaning more towards Bullet. But I don't know. I haven't really made that decision yet. Bullet is probably the one I'm going to go with, though. Let's see. Yeah, it is a huge task and definitely not a priority, especially when there's already ones out there that could do the job for me. I will be doing it in such a way where it is not tightly coupled to the engine. And so I'll be putting that through an abstraction layer so that if I decide later that I want to swap out what physics engine I'm using, I can do that. Okay, cool. All right, so last time we basically got to the point where we created our instance and our debug messenger. And it took a lot to sort of get to this point. But the next thing that we're actually going to do from here is get our devices created. And once we have our devices created, then there are steps to create our shader, and then create a swap chain, and then create render paths, graphics pipeline, command pools, all that stuff. So there's probably about 10 or 12 more steps after this point that we're going to need to cover. So hopefully we can get through all of those today. If we can't, it'll be on the next stream. But I'm really hoping to get something written to the screen today. Okay, so let's see. The next thing that we need to go ahead and do is we actually need to create a surface to render to. So right now, when we run our application, we're presented with this empty window. And what we need is a way to hook in Vulkan to this empty window to tell Windows to draw to it. And what that's called in Vulkan terms is a surface. So since it's tied to the window system, it is a bit platform specific. So creating the surface actually isn't going to happen in the renderer. It's going to happen in the platform. And so what we're going to do is we're going to start off by making a create surface method. So it's going to return type void. And we're going to create the surface. We are going to take in, I believe we need just the instance, if I remember correctly. So we'll take in the Vulkan instance. This is going to be something that I'm going to have to abstract later on, because I actually don't want to be passing Vulkan data around like this. But I don't have that that iRenderer abstraction layer yet. So unfortunately, I am going to have to pass the raw instance this way for now. And then we need to get a pointer to a vk surface khr. And we'll call that surface. So the way that this is going to work is the method will be called passing an instance, and then it will set this surface pointer or the value that the pointer points to, rather, to our surface object. And again, this is Vulkan specific. I'm not really too keen on leaving this here, but for now, that's what we're going to have to do. So let me just stub this out. Okay, so in order to create our surface, it's actually a really simple, straightforward call. It's actually GFLW is going to do that for us. And I do want to mention at some point, I probably will be swapping out GLFW for our own window handling code. It was just more convenient to sort of get things up and running. So thankfully, that's also all abstracted in the platform layer. So I don't have to worry about that affecting anything else. So we need GLFW create window surface. And we need, let's see, yeah, I was right, the instance. And then we need the window. And callbacks is no pointer as usual. And then the surface, we're just going to pass through as is. Okay, and since in this case this returns a VK result, we're actually going to wrap that in a VK check, which I actually don't have included here, so I'll need to add that include. I'll put it here. Vulkan utils. Okay, and that is all there is to creating the surface. Now, there's a lot of things that happen at the lower level here that GFLW is abstracting for us. At some point, we'll come back and tackle that stuff, but for now, it's way simpler to just handle it this way. Okay, so in the Vulkan Renderer, the next thing I'm actually going to save off here is the VK surface KHR. And something I didn't point out before, this KHR postfix that's there, that indicates that this is part of an extension. I forget exactly what the KHR stands for, Chronos something or other, but since surfaces are platform specific, it's not part of the core Vulkan spec. So it has to be loaded through an extension. So GLFW is actually loading that extension for us, but yeah, I just wanted to point that. So back in the renderer, all we'll need to do now is call platform create surface, pass it our instance and our surface. Sorry, a reference to our surface. There we go. Okay. So let me just build that real quick. Oh, I forgot to include Vulkan here. Okay, I'm gonna try running this real quick. And we don't see anything different. We didn't get any errors though either, so that's good. Cool, so that is all there is to the surface. Nice and simple. That's probably the simplest thing that we're going to be tackling today. Okay, so as I mentioned before, the next thing that we're going to have to do is we need to create our physical device. I should say select our physical device, and we'll need to create our logical device. So again, the physical device represents the GPU or GPUs that you have in your system, and the logical device is the application's view of that device. So typically, you don't actually reference or access the physical device. You'll access and reference the logical device. 95% of the time, I'll say. So we already have our variables here that we created last time. So the next thing that we'll need to do is we'll add a new method, and we'll call that select physical device. And then this case, a physical device Okay. And I'm actually going to make this private because nothing else outside of this should know about it. And I'll copy this over to our renderer. Okay. So the first thing that we're going to have to do is, again, this pattern of enumerating devices, or I should say enumerating in general. So we need a device count, and we're going to set that to 0. And then we'll call vk enumerate physical devices. And it's going to take the instance, a reference to device count, and a null pointer for the physical references. So we call this once in order to obtain the count, and then we have to call it again to actually obtain the devices. But before we do that, we need to create a vector of vk physical devices, because it is possible and highly likely that we will actually have more than one device. So we'll call this devices, and we will set it to be initialized with a capacity of device count. And then all we'll need to do is copy the enumerate physical devices, replacing this last null pointer with devices.data. Okay. We probably should do some checking here before we actually do this to make sure that we have a physical device. So I'm actually just going to add sort of a fail-safe in here to say if device count equals 0, that's a fatal error. So we'll say logger fatal, no supported physical devices were found. And that will actually crash the application because if we don't have that, we can't proceed. Cool. So the next thing that we're going to have to do is we're going to have to iterate each of these devices and take a look at the features that they have and select one that is suitable to our requirements. So we'll start off with a simple loop. We'll loop through all of the devices. So I less than device count plus I, and then I actually don't want to do this in line. I'm going to separate this out to a different method because it's actually kind of a lot of things that we have to look at. So let's create another private method. We'll call this physical device meets requirements. Not 100% happy with that name, but it'll work. And then we pass the vk physical device. Right, so this will simply return a Boolean indicating if this meets requirements. So back in the renderer, we will actually just, let's see. You know what, let's go ahead and fill this in now, and then we can always, that way we don't have to come back to it. So we'll say if physical device meets requirements, and then this is going to be devices I. We're going to return devices I. And then if we get here, we're just going to write a fatal message that also says no devices found which meet application requirements. And just for good measure, I'll return false here, even though we'll not actually ever hit that. The compiler may not see it that way. Sorry, not false, no pointer. Okay, so we're basically going to select our physical device by checking that it meets our requirements. So obviously the next thing that we need to do is we need to add a method to look and see if the device meets our requirements. Okay, so the very next thing that we need to do is we're going to have to do something called detection of Q family indices. And what Q family indices are is they are a numerical index that indicates how do I explain this? So it's the index of a queue that can be used for a specific purpose, such as the graphics pipeline or the presentation of an image to the screen, things of that nature. And so what we need to do is we actually need to query that our physical device has the capability to do those things, because it's quite possible we could get a physical device that doesn't support that for some reason, or at least doesn't support all the different things that we're going to need. Initially, it's going to be quite simple, but later on, we're going to be adding some advanced features that not all GPUs may support. So the way that we're going to handle this is we're going to need two things. We need an i32 for a graphics queue index, and I'm going to set that to -1. Oops. And that's basically going to mean that we did not find a graphics queue within this device. And then we're going to have a presentation queue index, which is going to be defaulted to -1 as well. And then we're actually going to need, I think I'm going to split this out into another method that does this for us, because we're going to actually have to use this a few times. And so let's go ahead and back to our header, and we'll create we'll do this void return type because we actually need more than one. We'll call it detect Q family indices, and it needs the physical device. And then it needs a pointer to an i32, which is going to be our graphics queue index. And then, as you may have guessed, we need another pointer to an i32, which is going to be our presentation queue index. Okay. And as we go, I'm going to be sort of explaining a little bit less and less of some of the things that I do commonly or repeatedly, like adding this every time. I'm not going to explain that every time anymore, just because it's too time consuming. So like I said, you guys will be able to grab this code. So if you miss anything, you can always rewind or grab the code, figure that out. Okay, so detecting Q family indices. So the first thing that we need for this is we need to follow our pattern again of getting the count of all of our Q families. So we're going to call this Q32 Q family count. Default that to 0. We're going to call vk get physical device Q family properties, and we need the physical device. We need to pass a reference to the Q family count and no pointer to the data. So same pattern as you guys have seen 100 times so far. Feels like 100 times anyways. So next we need a vector of those. So vk q family properties, and we'll call this, I guess we'll call it family properties, and we'll initialize it with a capacity of q family count. Next, we'll grab a copy of this, and again, paste it there, replacing the null pointer with a call to data. Okay, so the next thing that we're going to do is we're going to iterate through all of these things. So we'll need a basic for loop again, 32, I equals 0, I is less than q family count plus I. And now what we'll check is, does it support the graphics queue first? So we'll check for that. Does it support? So to do that, we will check the queue flags on the current family property to see if it has the graphics bit set. And if it does, then we can set the data that the graphics queue index is pointing to I. Nice and simple. And the presentation support is going to work somewhat similar. The only difference is we actually have to query for that. So we need a vk bool 32, which is we'll call supports presentation, and we'll default that to vk false. These are just this vk bool 32. We could use true and false, but there are a lot of places where Vulkan is actually expecting this to be a number, which if you look here, it actually expands to 0, and true is 1. And so we could do that, but I prefer to be a little bit more explicit, at least to the Vulkan calls themselves. The next thing is a call to vk get physical device surface support KHR. And again, we have that KHR postfix there to indicate that this is actually an extension method. So we pass it physical device, and I is the current index that we're passing. So we're saying check the current index that we're on to see if this is supported. We'll need to pass it a copy of the surface, and then we'll pass it a reference to supports presentation. And so this will basically take the current physical device, and then using the surface determine if that is capable of actually presenting. I'm not 100% sure where you would ever run into a situation where this wouldn't be true. Maybe in a server farm, like a render farm or something like that. That's about the only thing I can think of. If any of you guys know, feel free to let me know. Okay, so if supports presentation, then we can set the value that the presentation queue index is pointing to I. Okay, and that's all there is to detecting our queue family indices. So we basically, this is one way of at least detecting features that will kind of come up in several different places as we continue. So kind of get used to seeing that. All right. Let me just check the comments real quick here. No, the GUI is not going to be platform specific. So when I say the UI layer, at least as far as the engine's concerned, that's actually all going to be implemented in the engine itself. So the only thing that's platform specific, excuse me, is the windowing system that is used to actually draw our engine's contents to. Other than that, we're going to be implementing an entire UI system inside the engine. The only platform-specific part of it is actually getting the window and the handle to the window, and then the actual surface. Hope that makes sense. Cool. All right, so we're going to call our new detect queue family indices. We're going to pass it the physical device, and then we'll pass it a reference to the graphics queue index, a reference to the presentation queue index. Okay? And this will tell us if those things are supported. So the next thing that we're going to have to do is we're going to have to query for what's known as SwapChain support. And the SwapChain is basically what manages drawing different images to the screen. You have a front buffer and a back buffer. The front buffer is the one that's being shown currently, and the back buffer is the one that's being drawn while there's one being shown, and then they get flipped or swapped, hence the term SwapChain. And you can have more than 2 images. Most of the time, 2 is enough. We might do triple buffering at some point, but basically, we need to query support of that SwapChain so that we can figure out if it meets the requirements that we're going to need later on for the SwapChain. So to do that, we actually are going to create another method because I really don't, again, want to do all that in line. And so I'm going to call this, I actually need to create a structure for this. So before I create the method, I need a structure to hold the data that we're going to be using. So I'm going to create it here in line because the renderer is actually going to be the only thing that uses this. I may wind up moving this later on, but for sake of convenience, I'm going to put it here. I'm going to call this Vulkan SwapChain support details. And this is going to have VK surface capabilities KHR, which basically tells us what the surface is capable of. Capabilities. And then we're going to have a couple of vectors. So the first one is going to contain a list of formats that the surface uses. Wow, I spelled that wrong. VK surface format, KHR. I'm just going to call that formats. So this is a collection of the formats that the surface is capable of using. It contains color information, it contains image format information, things of that sort. And then we're also going to need a vector that contains the presentation mode information. So that is going to be in the form of a VK present info KHR. And I'm going to call that presentation modes. Okay, so we're actually going to be returning one of these, filling out and then returning one of these. So in our private methods, we want to go ahead and add a call this query SwapChain port. Yeah, that works. Okay, and again, we'll pass the device. I'm just going to okay. Query SwapChain support. Okay, and I'm going to go ahead and hook this up first, actually. So since this returns a support details, I'm going to call this SwapChain support, and I'm going to set it equal to query SwapChain support, passing the physical device. Okay, so that's going to call this guy, and this guy is going to do a little bit more looking at some of our properties. So the first thing we need to do is create a structure, and we'll be returning that structure. And next, we're actually going to have to get a count of the formats that are supported. Actually, I think I did. You know what? Let's do the capabilities first, since it's the first object. Let's do capabilities. And then we'll do surface formats, and then we'll do presentation modes. Okay, so for this we'll need vk get physical device surface capabilities khr, and we'll need the physical device. We'll need the surface, and we will pass a reference to details.capabilities. Okay, and that'll fill in that struct for us. Nice and simple. The next two things are going to follow almost the same pattern as each other, so we need to get a count first. So I'm going to get a format count, set that to 0. Say vk get physical device surface formats khr, and I'll pass physical device, I'll pass surface, and the count, so a reference to count, so format count, and null pointer. Spelled surface wrong. Okay. And then if the format count is not equal to 0, then we'll go ahead and resize the details dot formats to the format count, and then we'll take a copy of that line, same as before, plus details formats dot data. Cool. So again, it follows the same pattern of get the count, get the data. Presentation modes is going to be almost the exact same thing. So presentation mode count equals 0. vk get physical device surface presentation present modes khr rather. And here we're actually going to pass again physical device surface and a reference to present mode count, and of course null pointer for the data. Okay, so I'm this time going to resize presentation modes. Oops. Resize presentation mode count. This. To detail presentation modes data. Cool. And then this just returns. So if you take a look at this, you can kind of understand why I didn't really want to do it in line. It's much cleaner if it's just separated off. And eventually we probably can put things like this into like a utilities library where we don't have to have this taking up our main renderer space in our main renderer. Okay, so now that we have our Q family indices and our SwapChain support, now we can actually start looking at the properties of the device and the features of the device. So obtaining these two things is pretty simple. So VK physical device properties, and as you may have guessed, VK get physical device properties, pass the physical device and a reference to properties. And that's it, nice and simple. So the device features is actually almost the exact same thing. So I'm actually just gonna make a copy of this. And just rename this stuff. Okay, so there's the properties and the features. So now we'll have a bool called supports required Q families, and this will just be a simple check against two things. So it'll be graphics index is not equal to -1, and present Q index is not equal to -1. Okay. Let's see. So the next thing that we need to check is device extension support. And this is basically, it's device level extensions. So what we're going to do is get a list of all the extensions that the device has, and then we'll have a list of required extensions and compare them against each other and make sure that everything that is required is actually there. So similar to the pattern we've seen before, we have extension count. I can't type today either, it seems. And then VK enumerate device extension properties. And we'll pass the physical device. The layer name is going to be null pointer because we don't actually have a layer that we need to use. I'm not really going to go into that. That's kind of a deprecated thing. Device specific validation layers aren't really used past, I believe it was version 1.0. So that's always, at least as far as the foreseeable feature, always going to be null pointer. Let's see, the property count. So I need a reference to extension count, and then of course null pointer. Okay, and of course we'll need a vector of VK extension properties, and we'll call this available extensions, and we'll initialize that to capacity of extension count. Copy that. Extensions.data. Okay. So actually, let me just put a note in here. So these are the supported available extensions. And now we have a list of required extensions. And this is actually up to us. So in this case, it's going to just be a vector of C strings, so constant character pointer. We're going to call this required extensions, and we'll set that equal to a single one, which is going to be VK underscore KHR SwapChain extension name. There it is. And if we hover over that guy, we'll see that it's VKKHR SwapChain. So this is the extension that is required to create the SwapChain. The SwapChain itself, again, is platform specific, which is why it is an extension and not just part of the core API. Because it interfaces with the surface, which is platform specific, so it has to be platform specific too. But that's really the last layer of abstraction, rather, before we move on to the stuff that's generic across the board. Okay. Looks like we have a lot more chat here, so let me just see here. Hey, Black Knight Sprite, it's been a long time no see, man. Yeah, it has been quite a while since we've talked, actually. yeah, my hair was completely short last time. So why do game companies still use DirectX instead of Vulkan? There's a couple reasons for this. So DirectX, there's a lot of history with DirectX. Windows has always been sort of the primary gaming platform, at least as far as PC has gone. And a lot of large studios are familiar with DirectX. All their developers use DirectX. They're familiar with it. They can write products with it really quickly. And so part of it is just sort of grandfathering in because there's a lot of people that are already familiar with it and they don't want to have to pick up and learn something different. The same can be said for OpenGL. But there's also the fact that Xbox only supports DirectX. So if you're going to be writing code for DirectX, you're going to have to write if you're going to be writing code for Xbox, you're going to have to write DirectX code. And that is, of course, portable between Windows PCs and Xbox. You can use the same code base, so at least for the most part. So a lot of companies will do that, and then simply not support other platforms like PlayStation, for example. So I would say that's probably the biggest part of it, is just people know DirectX and they're familiar with it. And DirectX is really a first-class citizen on Windows. Vulkan and OpenGL have always been second-class citizens. OpenGL is barely a second-class citizen, I would say. It's only supported because the GPU manufacturers write drivers for it. But DirectX support is right out of the box. You include a header that comes pre-installed with the OS and good to go. You don't have to worry about any of the platform specifics. Yeah, I hope that answers that. OpenGL is popular than DirectX. Yeah, dude, Zooper, you pretty much answered it. Other than the bit about people just being really familiar with that. Difference between DirectX and Vulkan. Obviously, they're different APIs for different platforms. Vulkan is more platform agnostic, tries to be, whereas DirectX is tightly coupled to Windows and Xbox, so you can only use them there. Why only DirectX for? I think you're asking why is DirectX only for Windows, where Vulkan and OpenGL are cross-platform. That's because Microsoft owns DirectX. They develop DirectX, and they're the same ones that make Windows. So they're not going to support that outside of something on their own operating system. That's basically why. Cool. Oh, actually, it looks like I missed a couple. Did I write a plan for how all this is going to work before I started like an EDD? Kinda, in my head. I know how this is going to come together. I've written a bunch of game engines before, so I know how this is going to come together. But the idea behind this was to build an engine from the ground up without having too much design front loaded. And the reason for that is because I'm also hoping to not only show what my process is for developing engines, but also what my process is for dealing with issues that I run into along the way. And if I were to develop the whole thing up front, I think it takes away from that a little bit. So, yeah, hope that answers the question. Cool. Well, let's jump back into it. So, we finished off our SwapChain support. Now we've got our required. All right. So now we need to compare our list of available extensions to our required extensions. And this is going to be super simple. So we're going to have a success boolean. We may not actually need this, but yeah, we will. Okay. 64. So we're going to loop through all the required extensions. So I is less than required extensions dot size plus I. And then we'll have a tracker to see if we found the current one that we're looking for, and that is going to default to false. And we're also going to have a inner loop, and call this one j equals 0. J is less than do this the other way around. I guess it doesn't matter. Okay. I was thinking about maybe having this loop the other way around, but I think this way is fine. Okay, so I'm looping through the required extensions, which in this case is just going to be 1, and then I'm looping through our supported or available extension here. So we're going to do a string comparison, if I can type it correctly, between required extensions at the I index and available extensions at the J index. But in that case, we need to look at extension name. So we're basically just going to compare those two strings. And if they're equal to 0, meaning that they're exactly the same, then we can say found equals true and break. And that's going to break just this inner for loop. So we also need to say down here, if not found, then we need to say success equals false and break. So basically, if we've looped through all of our available extensions and we don't have the required extension that we're on, then this is going to fail and mark it as such. Cool. So next, we're going to create another bool where we'll say SwapChain meets requirements. And here's where we're going to check those SwapChain requirements that we got before. So first off, we'll say if supports required queue families, because we don't need to run this otherwise. Then SwapChain meets requirements is going to be equal to SwapChain support formats dot size being greater than 0. And SwapChain, and SwapChain support. We're also going to want to use presentation mode size. So we're basically going to say we're just going to do a blind check to make sure that we have at least one format and at least one presentation mode in our SwapChain support. And if we do then it's marked as being compatible with our current requirements. I want to leave a note here. There are other things we could look at. We could also look for a discrete GPU. We could score and rank them based on features and capabilities. So if you're ever looking to sort of auto choose a GPU, and you have multiples that meet your requirements that you could potentially use, and you want to pick the best one, you could do that right in the same section of code and just use some of these things to actually determine that. So our success of this is basically going to be a bunch of these booleans that we've created up to this point. Sort of all have to be true. So we have to support the required queue families. We have to have a swap chain that meets requirements, and we also want sampler anastrophe. And I'm not going to go into that right now, but it's something that we're going to need later when we start loading textures. And so I want to make sure that that gets added in there, because I could forget to add it later on, and that would be bad. Anyway, that is it for our check on physical device meeting requirements. So that should be it, as far as our physical device goes. So I'm just going to put in our constructor here a couple more notes. Create a surface select physical device, and now I can say select physical device. Okay, that's the physical device. So let's build this real quick. And oh, forgot to include the vector. Right. Let me see what I missed here. Query swap support should have. Oh, I'm passing this by reference, that I shouldn't be. I think that's it. Something up in the function call here. Physical device, surface, event mode count. Huh. That is interesting. Not completely sure why that's bleating. The wrong type in there, maybe? OKHR. Oh, yeah, that's exactly what it is. Okay, so this is expecting a VK present mode KHR, and my presentation mode is present info. Sorry about that. Transpose stuff sometimes, guys, it happens. Okay, so that builds. I'm actually going to go ahead and let me just go ahead and run this and see if we get a error here. We can't read something. Oh, I see the problem. Okay. When I queried this SwapChain support, instead of using the physical device I passed in, I used the physical device that the private member that hasn't actually been set yet. So this actually needs to be changed all the way down, which actually makes me think I also missed. Yeah, I called select physical device up here, and I'm returning the SwapChain, or the physical device rather, but I'm not actually setting it. So let me do that. Run again. Physical device is null. What did I miss? Oh, did it again. In fact, all of these need to be changed. This is the troubleshooting I was talking about, guys. All right. Anyway, so we have no errors, and our window is open. So our looks like our device is all set up correctly. No news is good news, I suppose. Cool. Let me check the chat again. Oh, a lot of stuff in here. Okay, I'm just gonna pick out a couple things here then. Is there any performance difference? Yes, there can be. I know in some instances DirectX is faster, and in some instances Vulkan is faster. OpenGL, I suppose, could be faster. It's really specific to the platform you're working on. I would tend to think that DirectX, at least on a Windows box, DirectX and Vulkan are probably almost always going to be faster than OpenGL. But I could be wrong about that. It depends is the answer there. Yeah, NVIDIA has better performance on DirectX. That is true. Yeah, if you want to contribute to this, definitely. It is going to be an open source project, so cool. Vulkan good with AMD? Yes, it definitely is. And interestingly enough, by the way, I'm actually running an NVIDIA GPU, and I don't really have any issues with it, but I do know that AMD tends to be better, at least at the moment. So, in terms of mobile, well, I know Mac doesn't have official Vulkan support. They have their own API called Metal, and that is what they sort of push. It's a Objective C based API, and I know there is Vulkan VK, or I think it's Molten VK, that sits on top of that and basically translates. So it is available for Mac. I don't know about the performance though. I would assume for the phones. You know, I actually don't know the answer to that as far as the phones. I do know Vulkan runs on Android. I'm not sure what you mean though about the old retro games and PlayStation or Switch. Yeah, I'm not sure. Okay. That would be my dog barking for some reason. He thinks he hears something outside, I think. Okay, so APIs used in PlayStation and Switch is a Vulkan. No. Yeah, good boy. Actually, I think he's asleep. He might be dreaming. So the APIs used in PlayStation is like their own flavor of OpenGL. So it's completely proprietary. Yeah, as far as I know, Vulkan doesn't actually run on that platform. At least not yet. Okay, cool. So the next step is to get our logical device set up. So I'm actually going to hold some of these because this is starting to get kind of long. At some point I actually need to probably ought to clean this up too, but I'll come back to it. All right, so create logical device. So the next thing that we're going to do is we're going to create a method to set up our logical device. So I'm going to put that at the end here. So we want a void create logical device. Going to take a vector. It's actually going to be a vector of C strings again. So, and then it's actually going to be, yeah, we'll take a reference. Okay. So in order to create our logical device, we're going to need a few things. But first and foremost, we need to actually pass in a list of the required validation layers. And this is going to help us when we are debugging things and trying to figure out why things aren't working. This is to make sure that the logical device that we're going to create supports those things. Because if it doesn't, we're going to have a very bad time. And we don't want that. So let me just add this to the header. And so creating the logical device is actually going to start off very similar to something we've seen before. We need a i32 graphics q index, which starts off as -1. So we're basically going to be detecting this again. I may clean this up so that we don't have to do this more than once. But for right now I'm just going to do it in line. So I'm going to call my detect Q family indices again, pass the selected physical device, graphics index, and the presentation index. The next thing I need is basically just a quick array of the indices. So I'm going to say index count is 2, and actually I'm going to make that constant because then I can use it. Yeah, I think I'm going to make this unsigned. So what I need is an array of these indices to be able to pass to our logical device when we create it. Okay, and since these are both signed, I'm going to have to convert them to unsigned. that'll make more sense here in a second. Okay, so the first thing that we have to do is we need to set things up. Jump into this right now. Yeah, okay. So we need to set up our device queues. And what device queues are is they are kind of what they sound like. I mean, they're exactly what they sound like. They're a queue that takes commands in and runs them in a given order, in the order that they're presented. And these commands can be populating various buffers with data. It can be a draw command, for example. And it basically just runs all these things through these queues. And so what we're going to do here is, in order to create the device, we need to create some information about the queues that we need the device to actually use. And so we're going to actually set up a couple of things in order to create those queues. So we need an array actually of vk device queue create info, and we'll call this queue create infos, and that's actually going to be set to the index count. Yeah, and I think I'm going to do this actually in a loop. Hold on one second. Getting a text. All right, sorry about that. So we're going to loop through. Index count. We're going to loop through and oops. We're going to loop through and create these create information objects. So this, fill out the S type, which is the DK structure type device queue create info. There it is. Okay. Just gonna copy that. So the queue family index is going to be set to the indices I. So we're creating one for each index. The queue count is going to be 1. The flags are going to be 0 because we don't have any specific flags. I think this is actually reserved for future development, if I recall correctly. So it's actually not used. Pnext. Pnext is basically if we want to chain this to another create info. We're not actually going to do that, so I'm going to set this to null pointer. And then we need a queue priority because it wants priority as far as what priority these queues should take when we have multiple queues running at the same time. We're not going to have that, but it still needs a priority anyway. So I'm going to set the priority to 1. Typically that's a 0 to 1 range, and it tries to prioritize operations in the queue based on that range and where this queue falls into that. But we're not using it, so I'm going to say 1. And then we have a reference to, or pointer rather, to an array of queue priorities. In this case, it's just going to be a reference to our queue priority. Whoops. Okay. So that's the information that will create our queues for us. And the next thing that we want to do is, I mentioned before that we want anastrophe support. We actually need to tell Vulkan that we want that support. And again, I'll go into that when we actually get to that part. I just don't want to forget to do it. Features, yeah.
we will zero initialize everything and then say device features dot sampler anistrophe equals vk true. And this is to request anistrophe. I always have trouble spelling that word. And as I mentioned before, we could just use true or false here, but this is the correct Vulkan way to do it, so I'm going to use that. Okay, so the next thing that we need is a create info for our device itself. So we need vk device create info, and we'll call this device create info. Copy that, and then we'll set the S type inline as we've done before. vk structure type device create info, and then the enabled layer count is going to be equal to cast to a U32. The required validation layers that we pass in up here, dot size. And then we also need the enabled layer names. We need that array, and that's going to be the required validation layers dot data. Okay. Again, this is for debugging purposes, so I'm actually going to put a to-do in here. Disable on release builds. We're probably going to need to add that in a few other places around the code base, but for now, I'll just leave a comment reminding me to do it. Okay, so the next thing, thankfully this is a lot shorter than the creating the physical or selecting the physical device. We're just going to create the device here. So we're going to make a call to vk create device, and that's going to take the physical device. The create info going to be device create info. Allocator is null pointer as always, and the device, which is going to be a reference to our logical device. Okay, and since this, I believe, returns a VK result, we need to wrap that in a VK check. Cool. And that's all there is to creating the device. Not a whole heck of a lot to it. So while we're here and we have this info as far as the queue creation goes, we're actually going to go ahead and create the queues at the same time. But before we do that, so that we don't have to make this call again, I'm actually going to save those things off. And to do that, queue family indices. Under Vulkan Renderer, I'm going to add, I guess here under the device, is a i32 graphics family queue index, and also going to have one for presentation. And I'm going to save these things off. Cool. And now I can create the queues. So, as I mentioned before, there is a queue for the graphics pipeline, and there is a queue for the presentation. And these things do happen asynchronously, so we are going to have to put some stuff in place to handle that. But for now, all we're worried about is actually getting the queue. So we'll say vk get device queue. And we're going to pass the regular device, or the logical device, not the physical device anymore. So this is sort of the transition point to where we stop using the physical device so often and we start using the logical device more. We're going to do one for graphics family queue index. And then the queue index itself is 0. So we're saying we're just going to grab the first one that's available. And we will save this off to graphics queue, which we actually need to create. So if I can spell. Okay. So I'll make a copy of this. Name this to presentation queue. And then back in the renderer, we need to create actual queues for this. So vk queue, presentation queue, make a copy of that. Name this to graphics queue. Cool. All right. Queue. Oh, I need to pass references. Okay. All right. And that is the end of the logical device creation. So let's go ahead and build this and run. And as you can see, we get no errors. So we are good to go. Cool. Now we can actually start getting into a little bit more of the interesting stuff. So the next thing that we're going to be creating is shaders. Oops, I actually didn't make a call to create logical device. Right. Yeah, let me fix that real quick because I had forgotten that. I'm trying to remember what the extension name was for that. I believe it was. Oh, we already have it here. Required validation layers. Just need to pass that through. Okay. No errors before because it actually wasn't being called. So, all right, that is not the case. So it looks like we have an error. And this gives me a good opportunity to show you why the validation layers can be super useful. So it looks like here that we've actually called graphics family queue index. We've passed that twice here. And that is more than likely the cause of the problem. But if we read through this, queue info count must be greater than 0. Queue info count greater than 0. That isn't. Okay. Let's close this out. And let's actually change this presentation queue family index. I don't know that that's going to fix it, but that definitely was wrong. Okay, so we're still getting not one of the queue families given. Okay, so this is where the validation layers really help us out, right? It says the queue family index equals 0 is not one of the queue families given via this. So it actually keeps track of what you've called and what you haven't called. And it knows whether or not you're actually using something that is valid. And this is a huge advantage when you're debugging, because sometimes this stuff could be a little bit tricky to figure out. It'd be impossible to figure out exactly what we'd done there if we didn't have that feedback. Okay. Well, let's stop the application. This is saying the create info. Queue count was 1. Let's Actually run this again so I can copy the error message. Okay. Paste that there so I can actually see what I'm doing. Okay. So Q create info count must be greater than 0. So I'm guessing that we actually missed. Oh. Okay, so we created these info objects to actually create the queue, but we didn't pass them through to our create info. That might help. So we need queue create info count, and that is going to be queue count. What was it? Index count rather. Right, and then we also need queue create infos, which is going to be the queue create infos. Okay, now it should work. Okay, and this time it runs, but it looks like we're still getting some sort of error. So let's see. Queue family index is not unique. Within queue, That is interesting. Okay, so it's basically saying that our queue indices that are passed in our queue create infos are not. So queue family index I. Let me debug this real quick and see. 0, 0. So these both return to 0. That's because well, I just realized there's actually a couple more things it looks like we are potentially missing from our create info. So we actually need p-enabled features, which is going to be device features. And we need enabled extension count, which is going to be 1, because we are actually passing in our extensions, but So the extension that we need enabled is actually the SwapChain extension name. So I'm just going to create a quick array here. KHR SwapChain extension name, and then set so without these things, that definitely would not work either. That may actually be part of the underlying problem. We are getting the same thing. This more than likely means that I missed something there. Let me double check this Q family indices, make sure that this is right. Should be, I mean, it looks fine. Setting the data, okay. Those indices should be able to be the same, because technically it is possible that we have one queue that supports both. Let me debug this function real quick. Yeah, this supports presentation. Right, so that should be. You know what? Sometimes it helps to just shift your focus for a minute. So I'm just going to check chat. Your computer specs and how much monitors. So I'm actually running a machine that is, I don't know, probably 5 years old at this point. I think it's got a, say it's like a GTX 950. Let me look, I don't remember. Yeah, GeForce GTX 950. And I have two monitors running at 1080p. And I've got 16 gigabytes of RAM. So, not a bad machine. Got a i7 processor. I don't remember which one, to be completely honest with you. But yeah, it's like 5 years old. Still plenty fast enough for what I do. Cool. All right, let's move on. So I'm just going to have a look through this spec here and see if I can figure out what is the deal. If any of you guys have any ideas, feel free to chime in as well. Let's see. I don't really understand why that's throwing that error, to be completely honest, because they should be able to be the same index. Nice feature. Oh, one thing that is going to be a problem. The next definitely has to be set to null pointer. Let's see what else does. Should be it. Maybe that was what the was. That is really strange. I don't know why it's complaining about that, because it should be able to be the same family index. Shouldn't be an issue. Not unique with it. Family index should be there on both cases. Costa, what do you mean when you say which programming language will the engine support? Do you mean like a scripting language? So I'm actually not, at least in the short term, planning on supporting any scripting languages. I might add one at some point, maybe Lua or something like that. I'm not 100% sure. But I don't know. I feel like the idea of a scripting language just adds unnecessary complexity to the application as a whole, and it's an extra layer that everything has to run through and deal with. So I'm probably not going to be adding any sort of game level scripting to this, at least as far as a scripting language goes. It's probably just going to be C++, at least at the beginning. Oreo, you were absolutely right about that. Game engine debugging sometimes is definitely not fun. But, I mean, that's one of the risks we run by doing this on live stream, right? Yeah, it sometimes does not pan out to be tons and tons of fun. All right, you know what? I think for now I'm just gonna go ahead and move on. And what I'll do is I'll come back to that later, take another stab at it, and if I manage to solve it off screen, I'll bring it up later. But I'm just gonna move on because I want to get into the creation of shaders. So if you guys aren't familiar with what shaders are, they are basically they are a programmable aspect of the graphics pipeline that allow you to control the way that things are rendered. And there is typically a vertex shader that basically takes your three-dimensional vertex data, your position, all that, and translates it into 2D coordinates on the screen. And then you have a fragment or pixel shader, depending on what API you're talking about, that actually is what is responsible for the color that gets drawn to the screen. And that's a gross oversimplification of what shaders are. There's a lot that goes into it, and we'll be seeing that. But long and short of it, they're basically what's used for 90% of effects in games. They're used for things like making items glow or affecting lighting. They could be used for full screen effects, all kinds of things. So we're going to be creating some shaders and then loading them up. But before we do that, we're actually going to need to do a little bit more setup with our project so that we can actually load our shaders from file. Excuse me. So the first thing I'm going to do actually is open up this folder. And I'm also going to open up my Vulkan SDK folder, because there is a couple things we're going to have to copy out of here. So the first thing that we're going to need is the utility that's used to compile our shaders, because unlike the way that OpenGL works, where you just basically have a flat text file that exists on your machine somewhere, and you load that in and compile it during runtime, Vulkan prefers that you compile the shader ahead of time into bytecode, and then that bytecode gets loaded into the engine and consumed. And so there are utilities that come with the Vulkan SDK in order to allow for that. So what we need to do is I'm going to take a copy of that utility and place it in the repo so it's nice and easy to access. You guys don't have to necessarily do this step, but I'm going to. So in the main folder, I'm going to create another folder, and I'm going to call this Tools. And I'll go ahead and paste this GLSLC in there. And that is copied from C Vulkan SDK version bin. And this is the application that's used in order to compile our shaders into the SPIR-V format, which is ultimately what we're going to be looking at. Okay, so the next bit is going to be a batch file. We're actually going to just create a new text document, and we'll call this compile shaders.bat. And I'm actually going to open this up in Notepad++. And let me just open this. There we go. Okay, and this is basically, for those of you that aren't familiar with batch files, you probably ought to get familiar with them if you're going to be doing a lot of programming on Windows, because it's a very powerful language that you can use to automate certain tasks as part of your build process. And we're actually going to automate part of that here. So what we're going to do is we're going to create a batch file that automates the process of compiling these shaders. So let me just, this I don't particularly remember the syntax of, so I'm actually going to pull up an example. I'm going to cheat a little bit. Pull up an example because okay. So this is actually a batch file that I've written for another project, but I'm going to go ahead and just kind of steal a copy of this one. What this does is it basically, this echo off basically says don't echo every command that we're actually inputting in here to the console. We only want to output the results of it. So normally the way this works is it's just like if you typed it into the actual command prompt yourself, it outputs a line. So each one of these lines is an individual command, and it would actually output, like for example, where I'm saying echo compiling shaders, it would actually say echo compiling shaders, and then on another line it would say compiling shaders. So @echo off basically says don't do that. And the @ symbol is here because echo off itself is a command, and the echoing of commands isn't turned off until after echo off actually executes. So the @ symbol is basically saying don't echo this line. So what this does is it checks to see if a build shaders folder exists, and if it doesn't, it creates it. And then what we're going to do is call the glslc.exe, and we are going to pass a F shader stage, which is vertex. So that's basically saying this is the pipeline stage that we're going to be compiling a shader for. And then we pass it the GLSL file, which we're going to be writing. GLSL, for the record, stands for GL shading language. And then we're going to pass a -o for output, and we're going to output it to build shaders main.vert.spv. So it's going to be in that spr-v format that I mentioned before. And we're going to do this twice. We're going to do it once for the vertex shader and once for the fragment shader. And then we're also just going to echo a couple things here to let us know what's going on, and then let us know when we're done. So that's all that's needed for compile shaders.bat. Now, up from the tools directory, right next to it, we're going to create a shaders directory. And in there, we're going to create these two files. So we want a main.vert.glsl. So I'm actually just going to copy this. Create a new text document, and we'll just name it main.vert.glsl. And then I'll create a copy of that and rename it main.frag.glsl. We're going to have code in our engine that'll actually, where we'll just pass the name of the shader that we want, and it'll append these things automatically for us. Cool. So what we need to do at this point is actually write our shaders, and the shaders themselves are actually going to be pretty simple and straightforward. There's not a whole heck of a lot they're going to do, at least in the very beginning. So we're going to start by writing our vertex shader. And the first thing we need to add is a £, and then version space 450. And this is basically saying that we're using the 4.5 version of the shading language. And again, I know it's a little bit strange that we're writing GLSL because we're actually technically, we're not using OpenGL, we're using Vulkan. But this program will actually take this and convert it from GL shading code to what Vulkan needs to understand. There also is one out there for HLSL. If you're more familiar with that, coming from a DirectX background, you can use that one instead. Okay, so the first thing we're going to need is a array of vector 3s. And a vector 3 is basically an XYZ position in the world. So we're going to be calling this positions, and we want a vector of 3 of them. I'll say an array of 3, just to be a little bit more precise. So we want an array of 3 vector 3s. And we will set the values for that now. So the syntax of GLSL, if you're not familiar with it, is pretty similar to C, where you basically declare the type and then a identifier for it, and then in this case the size of the array, and then we say it equals a vector 3 array, and here's where we actually fill in our values. So for each one of these, we'll then say vector 3, and I'm not going to go into why I chose these positions just yet until we actually draw to the screen. But for now, just sort of take this at face value. So the first position is -0.5, -0.5, and then 0. So X, Y, and Z respectively. The next one I'm going to set to +5, and then -5, and then 0. And the last one I'm going to set to +5, 0.5 again, and then +0.5 again, and 0. So basically this is going to create a triangle in 3D space. And that triangle is eventually what we're going to be rendering to the screen. It's not very complicated, not very interesting, I suppose, yet, but rendering a triangle is always sort of the first step to writing a graphics renderer. So next, we need an entry point. Just like C and C++, we need a main function. And you don't technically have to call it main. As far as Vulkan is concerned, you can actually call it anything you want, because we're actually going to tell Vulkan what the entry point is. But as a matter of standards, I'm just going to call it main. So the only thing that we're going to do here is we're going to call something, or we're going to set rather, something called GL_position. And the case sensitivity of this is very important. In fact, let me zoom this in a little bit, guys. Hopefully you guys can see that a little bit better. So GL position is the individual position of a vertex that's being converted to screen space. So this is the ultimate out position that will be fed eventually into the next stage of the shader. So in this case, we're going to say vec4 because GL position is actually a vector 4. We'll be getting into vector 3s versus vector 4s a little bit later on, but just take it at face value that positions in GL, DirectX, any graphics API are actually vector 4s, not vector 3s. So we need positions, and then we're going to use another variable that's provided to us called vertex index. And vertex index is basically it's the index of this array that's passed here. So 0, 1, or 2. And I do want to point out that typically you don't hard code to your positions in the shader this way. We're just doing this to simply get things stood up so that we can see something on the screen sooner rather than later. But ordinarily you would create buffers to pass this data in because you're going to have far too many vectors to ever pass them this way. I mean, this is hard coded. It's not flexible. You're not going to be able to write anything with it working that way. But for now, we're doing it for the sake of simplicity. So these positions, of course, are vector 3s. So in GLSL, when you call a vector 4, you can replace the missing indices by adding comma and then putting whatever you want the remaining indices to be. So you can actually split this up. Or you can say 1.0 and it basically just fills in the rest with 1.0. So in 3D coordinates, positions are, they have 1.0 in the last element, what's known as the W element. So you have X, Y, Z, and then you have a W element. And 1 typically denotes a position, whereas a 0 indicates a direction when talking about trees. But I'm not really going to go into it any further than that. Okay, so that is all that there is to the vertex shader. So I'm going to move on to the fragment shader now. And the fragment shader is where the coloring takes place. So similar to before, we're going to have a pound version 450. And then we're actually going to load an extension here. And it's called GL underscore ARB underscore separate shader objects. And we want to enable that. And I'm not really going to go into what this extension does, just take it at face value. We need it for now. And I'll go into that a little bit more in the future. So the next thing we need is layout. And layout is something that we're going to be covering quite extensively in the upcoming videos. A layout basically determines what the how the data is actually fed to the shader. So it determines where in memory that is, because we feed a whole bunch of things to the shader at once, and you guys will see that in the future. So the first thing we give it is a location, which in this case is 0 since it's the first one. But eventually we'll have multiples of these layouts. So it'll be 1 or 2, whatever. But in this case, we're just using the first one. And then we're going to create an output variable, which basically says this is the result of this particular shader. So we do that by using the out keyword. And then we want a vector 4 because what we're actually going to be outputting is a color. So we're going to call that out color. And the out color is red, green, blue, alpha. So vector 4, RGBA. So we need to output one of those. Similar to the other stage, we need a main function. And then we're going to set out color. For now, we're actually going to hard code it to something. So we want to set it to vector 4. Oops. Outside the parenthesis. So we're going to set this to 1.0, 0.0, 0.0, 1.0. Now, based off of what I said about the format of this, can you guys sort of take a guess at what color this is going to wind up being? If you had to just guess. So basically, this is going to give us red, right? So we're basically saying we want colors are in range from 0 to 1, 1 being the full amount of that color, 0 being none of that color. And the colors are added together to create a final color. So I should say the channels are added together to create a final color. So colors are additive. So you have red, which is maxed out. We have no green, no blue, and then we have full alpha. So alpha is just our transparency. If it was set to 0, we wouldn't see anything. If we set it to 0.5, we'd be able to see through it. It'd be somewhat translucent. Cool. So that is pretty much all that there is to creating our shaders for right now. So what I'm actually going to do is from this root folder, I'm going to open up a new terminal. And I'm actually going to run our tools compile shaders bat. And it looks like I have an error in my shader. So that's actually a good thing because you guys can see what happens when we actually get an error. So it's saying the main vert GLSL looks like a syntax error. So let's take a look at that. Unexpected left brace, expecting left parenthesis. Line 3. Unexpected. Complaining about this line. Oh, because I've conflated my syntax here. These should be parentheses, not braces. So there are subtle syntax differences between this and C++, obviously. Sometimes that can trip you up. So I built again. Our shaders are compiled. So now if I actually look in the build, we have shaders and we have our 2 SPV files. So these are going to be needed when we actually go to load up our shaders. So yeah, I'm debating whether to jump into that now or if I should take a quick break. Let's take a look at the comments real quick, actually. Okay, cool. So I'm thinking I'm probably going to take just a couple minute break away from the screen and then come back. Cool. See you later, Poria. Thanks for joining us. Yeah, so my computer specs, I went over that a little bit earlier. So yeah, you can rewind. I might type it all out later, but yeah, I already kind of went over that. So all right, I'm gonna take a few minutes, and I will be right back.
Okay. The next, what we're going to do is we're actually going to load up the shaders. Let me just get my bearings here. Okay. So to do this, we'll need to add a private method. We're going to call this create shader for now. And we're going to pass it a C string for a name. And what I'm thinking is we'll probably also keep a copy of the shader as well. So right below here, put a U64 shader stage count. Oops. So the shader stage count is basically going to represent how many shaders we have. So we're going to have two. We're going to have a vertex shader and a fragment shader. So we need a std vector. And in this case, it's going to be called a vk pipeline shader stage create info. So we're not actually necessarily storing the shaders themselves, but more so the creation info for the shaders, if that makes sense. So we'll call this shader stages. And let's go ahead and fill out create shader. Okay. So what we're going to do is we're going to load this one file at a time. And we're going to basically read the entire file in as a chunk, and then we'll feed that into a create info for each individual shader. We'll save those off, and then we will use them later on when we go ahead and stand up the pipeline. However, there actually is one more thing that we're going to need to create, which is a function to read the shader file. So I'm actually going to call this read shader file. And that actually needs to return an array of characters. It's going to take in a constant character array called file name, and another constant character array. Call this shader type, and then a pointer to a file size, so that we know how much content is actually in the shader file. So let's go ahead and copy that over, set that up. Cool. So as I mentioned, we're going to basically do a quick read of the file. But before we can do that, we actually need to build out the file name. And this is kind of what I was alluding to before, where we could just pass the name of a shader and construct the file name and load it automatically. Before we can do any of that, we need to add another include. So we need fstream. And that's for file stream, so that we can actually read the file in. This bit of code will probably wind up getting moved to some sort of utility method at some point. But for brevity's sake, I'm just going to do it here. Okay, so I'm going to create a character buffer that is 256 characters. And this is for the file name, because generally you're not going to have a file name that's longer
longer than that. If you do, you really need to think about your naming conventions. So next we need a U32, which is length, and we're going to set that rather equal to the result of sn print f. Sn print f. We need to pass that the buffer, which is going to be the target, the count, or basically the size, which is 256, and then we're going to pass it the format string, which in this case is shaders slash, and then we need a %s. %s is basically saying replace these two characters with a string that we pass in later. So after that, we need a dot, and then another %s. So we're going to pass in another string, and then another dot SPV. And the things that we're going to be replacing those %s's with, we're going to pass in here at the end. You'll notice there's a little ellipsis there. That basically says we can pass other things that get worked into this string. And that's what snprintf is really useful for. So the first one is going to be file name, and the second one is going to be shader type. So what we're going to wind up with here is shaders slash file name dot file type, or shader type rather, dot SPV. And that is how we basically construct that. Also, we're going to add a sanity check. So we're going to say if length is less than 0, which, sorry, not less than 0, equal to 0. Actually, does this turn? Yeah, it can be less than 0. That's what I thought. Okay. That needs to be in I32. So one thing that will occur if snprintf fails for some reason, like maybe the buffer is not large enough for the text we're passing in here, it'll actually return a negative result. So if the length is less than 0, that means we're in an error condition. So we need to treat it as such and say that there's been an issue reading the shader file. So shader file name is too long. Okay. One more thing that's a little bit of a C thing to do is we need to set the buffer at position length equal to a terminating character, a null character, to terminate the string. That is, if we don't do that, when we go to actually read the file in, that's going to cause problems. So the next thing we do is std if stream. So this is an input stream, if you will. So it's basically saying we're reading a file. We'll call that file, and we're going to pass it buffer, which is the file name. And then the mode is going to be std ios.ate. And we're going to OR that with std ios binary. And don't confuse this iOS with the iOS as in iPhone or anything having to do with Mac platform whatsoever, because this was around, I think, before that. It has absolutely nothing to do with it. So yeah, don't think that has anything to do with Mac, because it doesn't. Okay, so if the file is not open, so not is file open, then that also means that we have an error. So I'm actually just going to, copy that, and then say shader unable to open file, just to give us a little bit of feedback there. Next, we'll set the file size value to, that's going to be a U64, so we want to make sure that that's cast file.tell. Oh, yeah, equals. Okay.
So the way that this is working is this is basically this is saying we want to open the file at the end, and then this says that we're going to open the file in binary read mode. And then we check to see if the file is open. If it is, since we're starting at the end, tellg will actually tell us where we're at in the file, or more specifically the stream position, which ultimately is a 64-bit integer. And in this case, since we opened with the stream starting at the end of the file, that position is going to be the file size. So save off the file size, and then we'll create a character pointer called file buffer, and we will set that to a malloc to the size of file size. There's a lot going on here if you guys aren't familiar with malloc, but basically what this is doing is it's creating a it's allocating memory to the size that we specify, which is file size, and then I'm casting that to a character pointer so that we have the correct type here. And that is what we are going to actually read the file into. So next we'll seek to the beginning by passing seekg 0, and we'll do a file.read, and the character string it wants is going to be the file buffer, and then the count we're going to want to pass file size, so that way we don't overflow the buffer. And then we will want to close the file when we're done with it and return file buffer. Now, for those of you out there who understand how mallocs work, anytime you have malloc, you have to free that memory, because we are creating a memory allocation on the heap, and anytime you do this, you have to manually free that. So anything that calls this method will have to make sure to delete the array that is passed back, otherwise you'll have a memory leak. And this is not something that we're going to be calling a lot, so I mean, I guess it wouldn't be that huge of a deal, but we don't want to get in the habit of just allowing memory to leak all over. Nobody wants that. Okay, so that concludes read shader file. So the create shader, first we're going to start with a vertex shader. All right, so we're going to need a U64 for the vert shader size. That's going to be that file size that we need. And then we need a character array, vertex shader source. And we're going to set that equal to read shader file. And the name we're going to pass is we're just going to pass through our name here. Shader type in this case is going to be vert. And then file size is going to be a reference to vertex shader size. And that is all we need to do to read in the file and get the content that this needs. VK shader module create info. So as you may have guessed, we need a create info where we can then create a shader module. So call this vertex shader create info, and we will initialize that with an S type. So that's going to be VK structure type shader module create info. Okay, and this vertex shader create info needs a couple of things. So it needs to know that code size that we obtained earlier, which is a size t, which is a U64, same thing. So we'll say vert shader size, and then it actually needs a pointer to the code. So pcode equals, and we're going to cast this to a U32 array, and we'll call that vertex shader source. And that's really all that's needed as far as the create info goes. So next we can just say create vk create shader module, pass device create info, which is going to be our vertex shader create info, null pointer for the allocator, and our shader module, which we don't actually
I don't actually have that stored off yet. So I'm just going to say yeah, that doesn't need to be a class member. We only need it locally. So VK shader module, vert shader module. Great. Okay, so we have our create info. We fill that out, pass it our shader source, and then we go ahead and create our module. And of course, this returns a VK result, so we need to wrap that in a VK check. And that's pretty much all there is to setting up at least the shader module. So I'm actually just going to copy all of this and do the exact same thing for the fragment shader. I'm just going to change the name. And I'll change the name here. Here. And change this from vert to frag. And that should be everything that we have to do for that one. It's the same exact process. Okay. The next thing that we need to do is we need to set up shader stages. And the shader stages are sort of what I alluded to before, where you have various stages of the shading process. And vertex and fragment are two of those. So we need to actually set up those stages so that later when we go ahead and create the graphics pipeline, we can tell the graphics pipeline about these. So the vertex shader stage is a VK pipeline shader stage create info. And we'll call this vert shader stage info. And we will initialize that with VK structure type pipeline shader stage create info. Some of those get pretty long. Great. So this information needs three things. It needs to know what stage it is. So stage in this case is VK shader stage vertex bit. So this is what tells it that the stage that we're setting up is a vertex shader. It needs to know the module, which is this guy. And it also needs to know the P name. The P name is the name of the entry point. And it's kind of terribly named, to be honest, but when we were writing the shader and I said that you don't necessarily have to use main, this is what I was talking about, because we can actually tell it to use something else. But we're going to stick with main for this. And that's it. That's all that's needed for the stage creation info. So I'm actually going to duplicate this for the fragment shader. Rename this to frag shader stage info and fragment shader module. Okay, and now we have our shader stage count and our shader stages. So our shader stage count is 2, and our shader stages, we just push back our vert shader stage info and the frag shader stage info. Also, if you recall, I was saying that whatever is calling this read shader file needs to destroy the array that is used here. After we have actually created these things, we can destroy those safely. So we could just call delete vertex shader source and delete fragment Oh, that would have been a bug. This should be source, not size. Fragment shader source. And that needs to be, yeah. That's one of the dangers of copy and paste, is if you don't swap it out right. Okay. So fragment shader source. There we go. Okay. As far as standing up our shaders and reading them in, that's all we should have to do. So up top here, after create logical device, we say that we want to create a shader, pass main. So it makes this nice and simple as far as creating the main shader. Okay. Check the comments here. Okay. Will there be a level editor? Yes, but that's quite a ways off, quite honestly. There definitely will be one, but it's going to be a bit before we get to that. Wouldn't you want to return null pointers on errors also? Hi. Well, typically I would say yes, we should return null pointers on errors. However, the way that I have Fatal set up is whenever I use Fatal, it actually causes the application to crash. So I think in this case, I'm actually safe not doing that because the application is not going to get to that point anyways, but that's a good call. I might go back and fix that. Fragment code still using a vertex variable. Oh, that must be, yeah, okay. Yeah, you caught it before I did, I think. Okay, cool. Yeah, thanks for that. Yeah, that was a little bit weird, but it happens. You know, copy pasta for the loss sometimes. Okay. So the next thing that we're gonna need to do is we're actually gonna need to create the swap chain. I think before I get into that though, let me just run this real quick. Not. Oh, that's weird. Why did it? Didn't complain about this one, but it's complaining about that one. Here's another one I missed. That's why. Okay. Cool. So I ran it, and this is what I was talking about Fatal. It actually basically uses an assert false to crash the application. So unable to open file. That's thing. Let me debug that because that might indicate that this path logic here is incorrect. So see what that's generating. Shaders main vert SPV. Oh, I think I know what the problem is actually. I don't think the problem's with the code. I think the problem is actually in the project properties. When we are debugging, we need to change the working directory to use solution directory build, because that is where all of our assets are being copied to. Okay, So I think this is probably going to work, but yeah, it looks like it did. Okay. So let me continue that. Okay. So we still have the error that we had before. I still need to go back and fix that at some point, but our shader is loading correctly. Obviously, we still don't see anything on the screen here yet, but we're getting there. Okay, so the shader should be good to go. So the next thing that we need to do is create our swap chain. Let me see how long the stream has gone on for. So we're at about 2.5 hours right now. I think I might end this here, at least for a little bit. And I may do another one a little bit later today, I'm not sure. Or I may just save it for next week. Let me check that one more time. And another one. 312, yeah. I think that was the second one I found, right? Yeah. Yeah, that's one of the reasons that copy pasting can sort of kick you sometimes. So yeah, I think I'm gonna go ahead and cut this because it's already been 2.5 hours. I do want to continue this though. I was hoping to get something on the screen today, but there's a lot of steps and getting all this stuff stood up. And you know, Vulkan is quite verbose, so there's a lot of steps, and it takes a little while to explain all those things. So unfortunately, we didn't get there today, but I do think we could get there definitely on the next stream. I mean, let's see. So we would need to create the swap chain, some image views, render pass, a graphics pipeline, and then a command pool / command buffers, depth buffer, frame buffer, and semaphores and fences, and then we can create our draw. So yeah, there's still several steps to go. So I don't think I'm going to cover all that today. So what I think I'm going to do is I'll cut the stream short for today, and I'm going to research what this stupid error is here, because I really don't understand why I'm getting that, because I've never gotten that before by having two queues use the same index. That's never been a problem. I don't know if maybe that's a Vulkan 1.2 thing, but I'll get to the bottom of that and I'll bring it up in the next stream. So do you guys have any questions before I cut this short? Cool. I'm glad you guys found it interesting and informative. That's awesome. Yeah, it can be a little frustrating sometimes when you're debugging live, but cool. Thank you. Yeah, it's there's something about watching coding that can be satisfying for sure. I watch a lot of those videos myself. Let me take a quick look at my calendar and see. See here. So I'm thinking probably if I don't come back today and do another one, it'll be next week for sure. It'll likely either be Saturday or Sunday. If you guys follow me on YouTube, I can announce it there. I can also announce it on Twitter and also the Discord server. I've got a couple of places that I'll put that out. Yeah, it's almost midnight there. Yeah, that's crazy. You must be over in let's see. Where's that? Isn't that that's like Chinese time zone almost, isn't it? It's almost midnight there. India. Okay. Okay. Yeah, that's IST. Gotcha. Okay. I was trying to do it in my head, but okay, cool. Yeah, like I said, if I do wind up coming back today, it'll probably be in a couple of hours. If not, then next week for sure. But of course, these will be available on my channel as well. So go ahead. Yeah, I was pretty close, kinda. But yeah, follow me and like and subscribe if you haven't already, and I'll be announcing the next stream sometime shortly. Thank you guys for joining. I really appreciate it. Appreciate all you guys and all the feedback and everything. And yeah, cool. See you guys next time.